Hello everyone, in this video I'm probing the brains of AI. This is a simple model that figures out the resistance in Ohm's law. The input is I and the output is voltage. And here are samples. As you can calculate, the answer to R is 35, but I randomly put the number 3, and the model should figure out that R is 7, or the answer should be 7, because 1 times 7 is 7, 5 times 7 is 35, and 10 times 7 is 70. So it should figure out that R is 7. So I will run it. I'll uncomment this first. Now run it, and there it is. So it figures out that R is 7. I'll scroll so you can see as it starts learning. It starts out guessing 3, and then next iteration is 3.34, 3.3, or 3.64, 3.93, etc. And it gets closer and closer to 7. So that's showing that. So I can come down here, and if I redo the model, let's see, think it through real quick. So I can just simply put something times R is equal to something. Let's see what it'll do. Hold on. So 4 times R, it should be 28. 4 times R equals approximately 28. So if I say to put it in the right equation form, V equals IR. If I say I is 4, oops, if I say I times R, and come up here and do I equals 4, then it should show the same result. So V equals IR, and oops, make it print V. So 28, approximately. So that shows that it's working, and that's used for inference. Just another example of that it's working is 8. So 8 times 7 is 56. If I run it, it's 55.995, rounded off to 56. So that shows it's working. Now I'll break down what it's doing in a hierarchical view. So the whole model, it's figuring out what R is. And the inputs are the amps, and the outputs are the voltages. So when I put in 1 amp, the voltage is 7. And so 1 times 7 is 7. So the amps are I. So if I put in 1 amp multiplied by the 7 that it figured out that R is, that's 1 times 7 is 7, so the voltage is equal to 7. If I put in 5 as I, 5 times 7 is 35, so the voltage is 35. So I gave it 3 inputs and 3 examples of what the answer should be, and it figured it out. So now I'm going to probe deeper into this. So what I'm going to do here is make it print out the derivatives, and this is what I'm just basically researching at the moment to try to understand the simple examples, because once you understand those, then you understand the complex examples way easier, because the complex is made of a lot of simple things. Okay, so if I run this, I'm going to cancel out the R at that spot for the moment. Run it, and there we go. So R is 3.336, 3.64, etc. Then it gets better and better and closer to 7 eventually, as we saw before. But this time you can see each loop that's happening with the derivatives and with the output for each sample. So the derivative, remember the number R starts out at 3. So the update consists of, scoot that down and organize it. The update consists of, hold on, make it cleaner. Alright, so the update consists of taking whatever value R is, which is 3 to begin with, and subtracting from it a percentage, or learning rate, a percentage of the global derivative. So if the global derivative is negative 336, and the learning rate is 0.001, then you can multiply, well, you would be subtracting it, so subtracting a negative is the same thing as adding. So I'll just do the addition and clear this out. So it starts out at 3, so you have 3 minus the learning rate times the derivative. So 3 minus the learning rate of 0.001, then times the global derivative of the, remember we canceled out the negatives, so global derivative of 336, and that equals 2. Oh, sorry, my bad. I think I did the wrong sign. Okay, excuse me. So you have 3 minus, but the minus and the negative cancel, so it would actually be 3 plus. And then you have the learning rate of 0.001 times 336. 336, and that equals 3.336. And if you look over here, the updated R is 3.336. So now that we have that, you can say, do this again. So they're accurate this time, though. All right, so the learning rate. All right, so you have the R is currently 3.336. So subtract a negative sign that's adding. So add the learning rate times the global derivative currently. So the learning rate 0.001, and the global derivative is 307 or 307.78. So it equals 3.6437, etc. So rounded off to 3 decimal places would be 3.644. If you look right here, 3.644. And so that's how this is working. It just takes it starts out with the current, which is 3, or it starts out as 3 as R, and it subtracts from it a percentage of the global derivative, and that creates the new R. And then it redoes the neural net, and then it does the same thing again by subtracting from that current R the learning rate, or the percentage of the global derivative, which is negative, well, in this case it would be negative 307.78, and it creates the new R. Then runs through the neural net again to figure out the global derivative, and subtract from R the percentage of the global derivative, and it comes out to be this. And do it again and again and again. So the pattern is, whatever the starting R is, subtract from it the percentage of the global derivative, and that gives a new R, and then do it again and again and again. And that's how it learns what R is, and it figures out that R is 7. So that's part of how that works. Now, I'm going to check and make sure this is recording. Yay, okay. So that's a simple example of how this works. I'm part of it. But this other stuff I'm digging into as well, and I haven't explored this a lot yet, so I'll just do it right now. If you're familiar with it, just leave some comments and let me know what you think and if you've observed any patterns. Okay, so what this is doing, see, DLDR is the product of this times this, plus this times this, plus this times this. And this is for each sample. That's sample 0, sample 1, and sample 2. That's why there's 3 of them, and they're summed together. So this is DL_DVH0. So where is DL_DVH0? DL_DVH0. So this is the gradient, okay, for this part, the local derivative. This is the local derivative of this operation for this specific thing. Because here you would use multivariable calculus, and the way you do multivariable calculus is you figure out the, like a slope on a straight line graph, change y over change in x, except you make the change in x basically infinitely small, and then you just figure out the slope. So when you do that, it comes out to be, well, that's for regular differential calculus. So multivariable calculus is the same, except you count all the other variables constant except 1, and you only make a change in that one specific variable, that one specific number that the variable represents, and then you see how many times that change the end result changes. So just say if you increased, like this for example, if you increased, let's see, I is 1, so R starts out at 3, So if you bump up I by a tiny amount, how many times that bump up does this change? It changes by R. Or you can do the opposite and say if you bump up R by a tiny amount, it changes by this many times. So a specific example is if you increase R by 0.1, then you'd have 3.1. R would be 3.1. So then you'd multiply 3.1 by 1 in this case. 3.1 times 1 is 3.1. So then you subtract the original 3 that it would have been, the change in y. So you subtract the original 3, in other words, y2 minus the y1, and that gives you 0.1. And then you divide that 0.1 by the amount that you changed, that you bumped it up by. So if you divide 0.1 by the 0.1 you bumped it up by, that comes out to 1. And that's the local derivative for that. Another example without 1 is you bump up R again by 0.01. And I index 1 is 5. So you have, starts out at 3, so it becomes 3.0, or 3.1, sorry. So R is 3.1. So you multiply 3.1 by 5 equals 15.5. Then you subtract the original, see, what would it have been? 3 times 5 is 15. It would have been 15. So now you subtract the 15 from the 15.5, and that gives you 0.5. And then you divide that by the 0.1, and that comes out to 5. So the local derivative here is 5, and that happens to be what I is. And the same pattern follows for all of it. So that's the derivative for multiplication. And so it can be written like this, and that will adjust for any numbers automatically. Or, sorry, it can be written like, where is it? I wrote it somewhere. Yeah. It can be written like this. Like, this is VH0. In other words, the voltage hat 0. Typically in statistics, or sometimes in statistics, the output of a prediction is called Y hat because it has that little triangle arrow above it, not the greater than, less than, except you flip it and make it look like the arrow's pointing up and put it on top and it looks like a hat. So anyway, it's called Y hat. Anyway, so the prediction here is for V, though, so I just called it V hat. And this is sub-0, or V hat 0, to represent this zeroth example. Or sorry, this zeroth example. So you have this, the derivative of this with respect to, or in other words, an infinitesimally small increase in this is equal to this. In other words, d for derivative, or dv h0 dr is equal to I index 0. And then, that's that, etc. Okay. And this is the derivative for the squared error. So we take the squared error is the difference between the prediction and what the correct answer is. Like prediction minus correct answer. Like you picture it, spits out a prediction first, and then you subtract the correct answer from it. And so then you square that, and it matters what order it's in too, because if you notice down here, it's not squaring. The square basically gets rid of negatives. That's one of the things it does. But down here, when you calculate the derivative, this won't get rid of a negative. If this comes out to be -7 or whatever, then this will be 2 times -7. But if it's +7, it'll be 2 times +7. So it'll be -14 or +14, and those are different things. So it's important to get it correct. So you take the output of this, the output is what you put first, and then you subtract what the correct answer is in that order. And so this is the squared error right here. But since there's multiple samples, then you can take the mean of that, and it smooths things out and makes the calculations, it makes stuff work better. If you notice, it's like these multiple things converge into one. And this is where you're dividing it by the length of V, because there's 3 things added together. There's this, and this. And the length of V is 3 things. And so this automatically adjusts for how many things there are. And it creates one variable instead of multiple. So this is where they converge. And so down here, the gradient for all of this, and then you multiply the local derivatives together to get the global derivative. And since all of these feed into the same DLDR node, then you sum these together, and that gives you the global derivative for the whole thing. And then you can use that, like I was saying earlier, to multiply the learning rate by, and that will give you what to subtract from R, and so that it can update and eventually put out that R is 7 or whatever it's supposed to be. So that's kind of how that works. And there's some other things as well. Let's see. You can just look through here and see how it progresses along as the data changes. But if you notice that dvh0dr, see dvh0dr, remember I was saying it was I index 0, it doesn't change. That's because the derivative is the input, and the input doesn't change. The input to the neural net. So that's why it's 1, 5, and, hold on. Get back up here. Yeah, 1, 5, and 10. So see, in this iteration is 1, 5, and 10. This one is 1, 5, and 10, etc. All the way down the bottom, it's still, you guessed it, 1, 5, and 10. But some of the other things do change. As you can see, the loss doesn't change within that first loop, because the loss is one thing. See, this is figuring up, where is it? Hold on just a second. Yeah, this is showing dvh0 dr, dvh1 dr, dvh2 dr. So that's why those numbers can change. See, dvh1, yeah. That's why they can change within that one iteration of the loop. But the L is just one singular thing, so it doesn't change within that one iteration. It does change on the next iteration, and the next, etc. So that's the loss, and as you can see, it decreases until it approaches 0, or gets to 0. In this case, it looks like. So that's kind of how these things work. And dvh0, see what that is real quick. dvh0. Oh, this is the derivative for the mean squared error loss function with respect to the different inputs to it, like the vh0, vh1, and vh2. That's why it says dldvh1, dldvh0, dldvh1, and dldvh2. So, in summary, V equals IR. This is to figure out when probing into the brains of AI. And R, I set it to a random number, and basically gave it some inputs and outputs that use 7 as the multiplier, so it can figure out what 7 is. So in other words, 1 times 7 is 7, 5 times 7 is 35, and 10 times 7 is 70. And so gave it these 3 inputs, 3 outputs, and said figure out what R is, and I gave it a random number to start with. And then, as you can see, it went from 3 to 3.336, etc. And then it figured out, adjusting for rounding errors, it figured out what R is, which is 7. So if you have any questions or comments, let me know, and thanks for watching, and please click like and subscribe.